China just replaced silicon with insane new glass. The entire chip industry is shaken. Here is something that sounds completely made up. China has been quietly pouring over $1 billion into glass. Not oil, not rare earth metals, not the next generation of computer chips, glass. And because of it, some of the most powerful tech companies on Earth are now scrambling to catch up in a race they didn't even know they were losing. Now, before you click away thinking this is about windows or phone screens, stay with me, because the glass at the center of this story is nothing like anything you have ever touched or seen. It is engineered at a level of precision that would have seemed like science fiction 20 years ago. It is thinner than a human hair, flatter than anything nature can produce on its own, and it might be the single most important material in deciding who controls the next decade of computing power. Here is the wild part. This didn't sneak up on the industry because it was hidden. It wasn't classified. The factories being built, the patents being filed, the investment funds being deployed, all of it was public. It just wasn't being watched. Because for years, everyone who cared about the global chip competition was staring at the same thing. Transistors. Who can make them smaller? Who can print more of them? Who can push them to the next generation before a rival does? That conversation dominated the headlines, shaped government policy, and dictated hundreds of billions of dollars in investment decisions. And while that conversation was happening at full volume, a different conversation was happening quietly about the layer underneath the chip, the part that holds the whole thing together. The part that, it turns out, is now the most important battleground in the entire industry, and the part where the biggest early moves have already been made. That is the story. And once you understand it, the way you think about the chip competition shifts completely. If you're into stories like this, the kind that get underneath the headlines and explain what is actually happening before the rest of the world catches on, subscribe right now and turn on notifications. This channel covers the strategic moves that matter: materials, infrastructure, supply chains, the decisions being made today that will determine who leads the next decade of technology. Lithium supply chains, satellite networks, AI infrastructure, rare earth dependencies. We have covered all of it, and there is a lot more coming. Hit subscribe so you don't miss it. Now let's get into this. The foundation nobody talks about. To understand why glass has become such a massive deal, you first need to understand what it is replacing. And to make that clear, think about a city. A big modern city. Skyscrapers, subway lines, power grids, fiber optic cables running under every street. You can look at that city and appreciate how impressive it all is. The architecture, the engineering, the sheer scale of what humans built. But none of it functions if the ground underneath shifts. The moment the foundation moves, everything built on top is compromised. It doesn't matter how elegant the design is or how much money went into the construction. A shaky foundation is a problem that no amount of clever work above ground can fix permanently. Computer chips have a foundation too. It is called a substrate. It is the base layer that the chip sits on. It holds everything in place, routes electrical signals between components, and helps manage the heat that chips generate when they run. For about 50 years, these substrates have been made from engineered plastics and resins, layers of synthetic materials bonded together into something that looks, if you could hold it, a little like a very sophisticated and very thin piece of laminated material. Not glamorous, not the kind of thing anyone makes a marketing video about, but essential in the same way that concrete footings are essential to a building. For most of chip history, this was perfectly fine. Early chips were compact, the demands were relatively modest, and the substrate did its job without complaint. The problems only started showing up when the chips got dramatically more complex, and they got dramatically more complex because of artificial intelligence. The chips powering today's most advanced AI systems aren't single chips anymore. They are clusters of smaller chips, called chiplets, bundled together into one enormous, densely interconnected package. Engineers build them this way because it lets them combine different types of chips into a single system. Memory chips, processing chips, communication chips, each type optimized for what it does best, all working together in one unified package that performs far beyond what any single chip could achieve alone. It is genuinely brilliant engineering. But it introduced a problem that only gets worse as the systems get bigger. Some of these chiplet packages now stretch beyond 8,000 square millimeters. Wrap your head around that. That is roughly the size of your phone screen. Now imagine that surface is packed with billions of microscopic connections, all trying to exchange data simultaneously at speeds measured in hundreds of gigabytes per second, while generating the kind of heat that would shut down a laptop in seconds. The engineering complexity involved is staggering, and at that scale, the substrate underneath stops being a passive holder and becomes one of the most critical performance variables in the entire system. Here is where the problem shows up. Plastic warps. Is not rigid in the way that truly matters here. When a plastic substrate heats up during operation, it expands slightly. When the chip powers down and it cools, it contracts. That cycle happens thousands of times over the lifespan of a chip. Each individual cycle involves movements that are almost impossibly small. We are talking about shifts measured in fractions of a millimeter. But at the scale of a modern AI chip package, with connections so fine they make a strand of DNA look like a rope, those tiny shifts accumulate into a serious problem. Connections that were perfectly aligned during manufacturing start to drift. Signals that should travel cleanly begin to distort. Performance degrades in ways that are inconsistent and hard to diagnose. In the worst cases, the connections break entirely and the chip fails. And the truly frustrating thing about all of this is that you cannot see it happening. There is no visible crack, no obvious moment of failure. The damage is invisible right up until it isn't. Engineers have spent years fighting this with clever design choices, tighter manufacturing tolerances, and increasingly sophisticated quality controls. Those approaches worked well enough when chip packages were smaller and the demands were lower. But the next generation of AI chips is going to push into territory where those patches simply cannot hold. The substrate material itself needed to change. And the answer that the industry arrived at, after years of material research, failed experiments, and manufacturing breakthroughs, is one that still surprises people when they first hear it. Why glass changes everything. Glass is such a counterintuitive answer to this problem that it's worth taking a second to sit with just how strange it sounds. Engineers are talking about building the foundation for the world's most powerful AI systems, devices running at extreme speeds under extreme heat, handling workloads worth billions of dollars, and the solution they're pointing to is the same basic material that gets swept off kitchen floors after accidents. Except it really, truly is not the same material at all. The glass being used in next-generation chip substrates is a precisely engineered product developed specifically to meet the demands of semiconductor packaging. It shares the same basic chemistry as window glass, the way a Formula One race car shares the same basic idea as a bicycle. Technically related, practically a completely different thing. Here is the clearest way to understand what makes it special. Think about what plastic does under heat. It behaves like a rubber band. Stretch it, release it, heat it, cool it, and over time it loses its shape. It fatigues. The material becomes less predictable with every cycle it goes through. At small chip sizes, that unpredictability is manageable. Engineers can account for it in the design. But at the package sizes that next-generation AI chips require, those 8,000 square millimeter monsters, unpredictability is a design-breaking problem with no clean engineering fix. Glass under the same conditions behaves more like a steel rod. You can heat it, cool it, run it through thousands of thermal cycles, load it with mechanical stress, it barely moves. Its dimensional stability is dramatically better than any plastic material currently used in chip packaging. That stability has a direct and measurable consequence. Engineers can place electrical connections far closer together without worrying those connections will drift out of alignment over the lifetime of the chip. Here is the number that stops people cold. Glass substrates can support up to 10 times more interconnect density than today's best plastic substrates. Not 10% more. 10 times more. That is not a meaningful upgrade. That is a generational leap. 10 times more connections in the same physical space means chips that can exchange data faster with less energy lost in transit, across greater distances within the package, with better signal fidelity than anything possible with plastic underneath. Think about what that actually means in practice. The performance ceiling of an AI chip is not just determined by the quality of the transistors inside it, it is also determined by how efficiently data can move between the different components that make up the system. If the connections between chiplets are slow or lossy or limited in number, the chip underperforms, regardless of how advanced the transistors are. The substrate is the communication backbone of the entire package. Improve the substrate dramatically, and you improve the whole system dramatically, even if you never touch a single transistor. The thermal story reinforces this. Glass conducts and distributes heat in ways that make thermal management easier as package sizes grow. Heat is one of the primary performance constraints on any chip. The faster you push it, the more heat it generates, and if that heat can't be removed fast enough, the chip throttles itself to avoid damage. Better heat management means you can run chips at their peak for longer, extracting more actual performance from the same hardware. Signal quality adds another layer. Electrical signals traveling through glass experience less interference and less loss than signals traveling through plastic. At the data rates that next-generation AI chips operate, rates that were unimaginable a decade ago, even small differences in signal integrity compound into real-world performance gaps that software cannot close. So why didn't the industry switch to glass substrates 10 years ago? Because making them is extraordinarily hard. The glass must be flat to tolerances that would be invisible to any measuring instrument outside a specialized metrology lab. The holes drilled through it to create electrical pathways, called through-glass vias, are smaller than a human hair and must be placed with perfect precision. Drilling holes through glass at that scale without introducing microscopic cracks that could propagate and cause failures weeks later is a manufacturing challenge that has taken years of dedicated engineering to even approach. That difficulty is not a footnote. It is the entire reason this story matters. The companies and countries that can solve the manufacturing problem at scale will control the next layer of the semiconductor supply chain. And the race to solve it is already underway and further along than most people realize. The billion-dollar pivot nobody was watching. For the better part of the last decade, the dominant narrative in the global chip competition came down to a single machine, the extreme ultraviolet lithography machine made by a Dutch company called ASML. It is the only machine on Earth capable of printing transistors at the most advanced scales. Without it, you cannot make a leading-edge chip. The United States and its allies spent years constructing an export control system designed specifically to keep these machines from reaching certain countries. The logic was clean and airtight. No advanced lithography machine, no advanced chips. Block the machine, block the progress. What that framing missed is that it was optimized for one specific path to more powerful computing, and that path is not the only path. Advanced packaging, specifically the substrate layer, is a completely different path, and it does not require an ASML machine. It requires material science, precision manufacturing, process engineering, capital, and patience. All things that can be developed independently without access to any export-controlled equipment. When you look at it that way, the decision to pour serious investment into glass substrate technology is not just a technical choice. It is a strategic repositioning toward a part of the semiconductor supply chain where the rules of the competition are fundamentally different. The investment has been substantial. China's national semiconductor investment funds have been directing capital specifically toward advanced packaging infrastructure since 2023. Multiple companies, multiple programs, all targeting glass substrates, the total crossing $1 billion across factories, equipment, patents, and talent development. None of it classified, all of it publicly registered. Just not generating much Western press coverage because the press was focused on lithography and transistor nodes. The company that makes this strategy click into focus most clearly is BOE. BOE is one of the world's largest manufacturers of display technology. They make the precision glass panels inside hundreds of millions of smartphones, televisions, and computer monitors every year. That is not a trivial business. Running it requires a large-scale precision glass manufacturing infrastructure, specialized equipment, deep process knowledge, supply chain relationships, and engineering talent built up over decades. And here's the thing that makes BOE's move into semiconductor-grade glass substrates so logical. That infrastructure overlaps significantly with what glass substrate production requires. The equipment used to manufacture precision display glass is related to the equipment used to manufacture precision substrate glass. The process knowledge transfers. The engineering teams have relevant expertise. The supply chain relationships are already in place. For BOE, this is not a reinvention of what they do. It is an extension of a capability they already build at massive scale for a different application. Their program targets production-capable glass substrate output running into 2026 and accelerating from there. Other companies have been working on specific technical pieces of the puzzle. The through-glass via challenge, drilling those hair-thin holes through glass without cracking it, has been the target of focused engineering efforts with real resources behind them. Progress is visible in patent filings, technical presentations at semiconductor conferences, and production roadmaps that name AI chip customers in the 2026 to 2027 window. What makes this whole approach so effective as a strategy is the timing logic. The transition from plastic to glass substrates hasn't happened yet at volume. It is coming, and the industry broadly agrees it is coming, but the factories producing glass substrates at scale for major AI chip customers do not fully exist yet. Whoever builds those factories first solves the yield problems first and qualifies with the major customers first. That company and that country's industry will have the kind of first-mover advantage in a capital-intensive precision manufacturing sector that is almost impossible to dislodge once it takes hold. It is the same dynamic that made TSMC the unchallenged dominant force in chip manufacturing for 20 years. When TSMC built its lead in the 1990s and early 2000s, it looked like an incremental advantage. By the time the rest of the world fully appreciated how dominant TSMC had become, the lead had compounded into something structural. Glass substrates are at an earlier stage of that same compounding curve right now. How the rest of the world is waking up. When a shift this significant starts gaining momentum, the rest of the industry does not stay still indefinitely. The response from major players in the United States, South Korea, and Japan has been accelerating, and it is more serious and more substantive than most people watching from the outside realize. Intel is the company with the longest track record in glass substrates of anyone in the world. Their program goes back over a decade, which in semiconductor time is an eternity. In that span, they have built one of the most extensive patent portfolios in the field, worked through manufacturing challenges that most competitors have not yet encountered, and developed a depth of process knowledge that only accumulates through years of hands-on engineering, trial and error, and failed experiments that teach you things you couldn't have learned any other way. More recently, Intel shifted its strategy toward licensing. Rather than trying to control glass substrate production directly, Intel's sharing its technology with manufacturing partners and suppliers, positioning itself as the intellectual property backbone of the emerging glass substrate ecosystem. It is a smart move for a company going through a significant period of restructuring in its own manufacturing business. Even if others run the production lines, Intel captures value from every line that runs on its technology. It is a bet on being the foundation of the foundation. Samsung's position in this race is further along in production readiness than most outside observers appreciate. The company is running an active pilot production line at its Zhejiang facility, not a research project, an actual pilot line staffed with engineers specifically hired for their glass substrate expertise. In late 2025, Samsung Electromechanics signed a formal materials partnership with Sumitomo Chemical, one of Japan's largest specialty chemical companies, to secure the supply of specialized glass materials the manufacturing process requires. Their internal roadmap targets commercial-scale production capability around 2028. That would make Samsung one of the first volume suppliers of glass substrates to major AI chip customers, and given how much of the global AI chip supply chain already runs through Samsung in one form or another, that is a significant position to occupy. TSMC controls roughly 90% of the world's advanced AI chip packaging capacity today. That level of dominance, built over decades of investment and process development, is genuinely hard to overstate. But TSMC also understands better than almost anyone that dominance in semiconductor manufacturing is never permanent. The landscape shifts, the technology transitions, and the companies that stay dominant are the ones that see the transition coming and position themselves ahead of it. In 2024, TSMC revived its glass substrate research and development program, a decision that sent a clear signal to everyone watching. This technology has graduated from interesting experiment to genuine strategic priority. When TSMC treats something as a priority, the broader industry takes notice immediately. Corning is a different kind of player, but an equally important one. Most people know Corning from Gorilla Glass, the protective coating on phone screens, but Corning's real expertise is in specialty glass manufacturing across a wide range of industries: fiber optic cables, pharmaceutical containers, aerospace applications, scientific instruments. That depth of materials science knowledge positions Corning as a potentially critical upstream supplier, the company that produces the raw semiconductor-grade glass that substrate manufacturers then process into finished products. Their investment in this space signals that the supply chain needed to support large-scale glass substrate manufacturing is beginning to form in the United States, and that matters enormously because a production ecosystem is only as strong as its weakest supply chain link. What the whole picture adds up to is a race that is genuinely and completely undecided. No single company or country has locked up the glass substrate market. The infrastructure is being built simultaneously right now across multiple continents, but the window for establishing leadership is not unlimited. The hyperscalers and AI chip designers who will drive this market, the companies building the data centers, training the AI models, designing the next generation of processors, will begin qualifying substrate suppliers over the next 2 to 3 years. The companies that are ready when that qualification process begins will land the contracts. The contracts will fund the process improvements. The process improvements will drive better yields and lower costs. And better yields and lower costs will lock in the customer relationships for the next decade. First mover advantage in precision manufacturing does not just mean getting there first. It means getting there first and then having every subsequent year of production make you harder to displace. What gets built on this foundation? Here is a pattern that shows up consistently in technology history. The most consequential shifts almost never look consequential when they're happening. They look small. They look technical. They look like something that belongs in a trade publication rather than a front-page story. And then years later, everyone who missed it looks back and sees clearly what they were looking at. They just didn't recognize it. The transition to glass substrates has that quality. The chip competition has been fought loudly and publicly for years, with export restrictions, government subsidies, and front-page stories about transistor sizes and fab capacity. All of that is real. All of it matters, but has also created a kind of tunnel vision, an intense focus on one layer of the semiconductor stack that made it easy to overlook what was happening in the layer below. The substrate is being reinvented right now, and the consequences of that reinvention will ripple through everything that runs on advanced chips. AI training is the most immediate application. The models that power the AI tools you use today are trained on enormous clusters of chips running for weeks or months at a time, burning through vast amounts of electrical power. Better substrates allow those chip clusters to exchange data faster with less energy wasted in transit. That translates directly into training runs that finish in less time, which translates into faster model development cycles, more experiments per year, faster iteration on ideas. The companies with access to better packaging infrastructure will develop AI capabilities faster than those without it. Data centers feel it too. The cost and energy consumption of large-scale AI infrastructure are two of the biggest constraints on how quickly AI capabilities can be deployed at scale. If better substrates allow data centers to pack more computing power into the same floor space and run that power more efficiently, the economics of AI deployment change. The cost of running large AI systems comes down. More applications become economically viable. More companies can afford to use advanced AI tools. The technology reaches further into more industries faster. The cascade goes wider than AI. Drug discovery programs that run on high-performance computing clusters benefit from faster underlying hardware. Climate modeling, material science research, defense applications, scientific computing across every discipline, all of it runs faster when the foundation improves. These are not hypothetical future benefits. They follow directly and mechanically from the performance improvements that glass substrates unlock. And here's the economic reality that makes the current window so difficult to recover from if you miss it. A single glass substrate production line costs between $500 million and $1 billion to build. That investment takes years to qualify with customers. The qualification process itself is lengthy because the customers, the chip designers, and AI hardware companies need to validate that the substrate performs reliably at scale before they commit their products to it. Whoever reaches volume production first gets into that qualification process first. Whoever completes qualification first gets the design wins. Whoever gets the design wins, accumulates the production experience that drives yields up and costs down. And there it is again, that compounding. Higher yields mean lower cost per unit. Lower cost per unit means more competitive pricing. More competitive pricing means more market share. More market share means more production volume. More volume means more experience. More experience means higher yields. The loop closes and tightens with every year of production. Companies outside the loop are not just behind, they are falling further behind with every passing quarter. It is the exact same dynamic that turned TSMC from a scrappy contract manufacturer in the 1980s into the irreplaceable backbone of the global chip industry by the 2000s. Not overnight, not through any single dramatic breakthrough. Through consistent early investment in a capability that compounded relentlessly over time until it became something no competitor could replicate without decades of their own compounding. The silicon era of computing, 50 years of progress driven by shrinking transistors, is not ending, but it is being joined by something new, a second axis of improvement, a new way to make computing systems dramatically more powerful that does not depend on making transistors smaller. It depends on making the foundation underneath them dramatically better. And the material that makes that possible is one that's been around for thousands of years. Flat, precise, stable under heat, invisible to the conversation until it suddenly wasn't. The AI era may well be built on glass, and the race to own that foundation, to be the company or the country that controls where the substrate gets made, how it gets made, and who gets access to it, is being decided in the years between now and 2028. Not in some distant future policy debate, not after the next round of export controls gets written. Right now, in factories being constructed and supply chain agreements being signed and patent portfolios being built that most people have never heard of. That is what makes this moment so unusual. The outcome's not locked in. The lead that exists today is real, but it is not irreversible. The companies and countries that recognize what is happening and respond with the seriousness it deserves still have time to shape how this plays out. The ones that keep staring at the transistor race while the substrate race runs in parallel may find themselves in a position very similar to the one that a lot of chip companies found themselves in when TSMC's lead finally became undeniable, surprised and very late. Here is the question I genuinely want your opinion on, and I want you to be honest, because people get heated about this one. Is it a good thing that one country is pulling ahead in a technology this foundational? Or does the world actually run better when no single nation controls the infrastructure that everything else depends on? There's a real argument on both sides. Some people say competition between countries drives faster innovation and pushes everyone to build better things. Others say that when critical technology gets concentrated in one place, the rest of the world ends up in a position it can't negotiate its way out of. Both of those things have historical evidence behind them. So drop your answer in the comments. I read every single one, and I genuinely want to know where you land on this. If this story made you think differently about what is actually happening in the chip world, hit the like button right now. It takes 1 second, and it genuinely helps this channel reach people.